Hi, I'm Dave Bearing, Technical Director here at TriStar, and welcome to another Tech Talk. Today we're going to be talking about composite bearings, and specifically three different styles of composite bearings that we make here at TriStar. Now, when people hear composites, the first thing they think is expensive. People consider composites the things that they put on aircraft and missiles, and now they're making bridges out of composites, and those types of composites can be very pricey. But the types of composites that we manufacture are very competitive and really geared for the industrial market, specifically for bearing applications. So let's take a look at the three different families of composites that we offer at TriStar. First of all, let's understand what a composite bearing is. It is generally defined as a high-load, self-lubricating, non-metallic plain bearing. These are sleeve, flange, thrust, slide pads, all self-lubricating, different types of lube systems available in each one of these different families. So we'll be taking a look at how those actually work and why we use the lube systems that we use. All of these are polymeric, so they are really going to be geared towards their limitations as a polymer, and we'll talk about those as well. The three different distinct families of composites that we manufacture are, first of all, UltraComp, which is our family of laminate wound products, such as this. This is our highest load bearing material, the UltraComp is. The second family is our CJ product, which is a filament wound material. And then finally is the TriSteel. And while this doesn't look the same because it's not really all polymeric as these two all are, the liner materials that we use are in fact polymeric. And it's a composite because it's a multiple of layers of material to make up this particular product. So in a sense, it's a composite. Now first we're going to talk about UltraComp. UltraComp has been around for many years now at TriStar. It's our trade name for a family of materials, all laminate wound, all self-lubricating. These are true self-lube bearing materials because in the case of the UltraComp, it is a bearing grade material through and through. Other composite materials, even like our CJ and the TriSteel, were really limited to a certain surface area, a certain thickness of the surface as its bearing grade material. In the case of UltraComp, however, the entire wall of material is in fact a bearing material. We have UltraComp in several different grades. Our most popular is the UC200, which is what this material is. It's a graphitized material. We also have a new flame-resistant version of the UC200. We have UC300, which uses PTFE as its lubricant. We also have a new AR grade PTFE, which has an additive in it to give it better abrasion resistance. UC400 is our moly-filled material, primarily for marine applications, and then UC500 is actually a blend of fabric, fibers, and different lubricating media. The primary attributes of UltraComp are basically strength. This is the highest compressive strength material of any polymer in a static condition on the market. This will take static conditions upwards of 55,000 psi. Now remember, I'm saying static. That doesn't necessarily translate to what it will do as a dynamic bearing, but from the standpoint of its maximum crush potential, 55,000 is the point at which we consider a static failure. We have in fact taken it beyond that. We've had tests to go as high as 70,000 psi before we saw a true catastrophic failure. However, for design purposes, we tend to work around yield pressures, or the psi and compressives, and that is generally between 18 and 23,000 psi. So from a design standpoint, looking at it purely as a dynamic bearing, our true number that we work with is, again, that 18 to 23,000 psi number. The UltraComp has very good abrasion resistance. It's very, very good material outdoors in dirty environments like in ag equipment, railway equipment, off-road construction equipment. Very, very adequate material for that environment. Again, it's not a lubricated material, so it does exceptionally well in that area. If you were using a lubricated bronze or even a lubricated hardened steel bushing, which most of those applications use, the downside is that once you get abrasive materials into that grease, if you're not properly purging it, it becomes a lapping compound and destroys even those hardened steel bushings and pins. And that gets a little pricey. So nice insurance policy here to have an unlubricated but very capable bearing material in the UltraComp. The other good thing about this material is it has outstanding vibration and impact resistance. This UltraComp material has a impact strength of over 20, which is extraordinary for a polymer. If you look at things like cast nylons, like Nylotron and similar products, they're down in the 3 to 4 range. Even micartas, which are not really classified as bearing grade materials, are 7 to 8 impact strength. So very, very high impact strength. So if you've got applications where you've got a lot of vibration going on, a lot of side loading and impacting, UltraComp is really an excellent call for that application. Some of the other attributes: temperature range from cryogenic to 335 degrees in some of the grades. Some of the grades also are limited to 265, 270 Fahrenheit. So you need to check with us on those situations. But usually these materials are being used in outdoor applications, so we can design around, minus 40 or minus 50 in northern Calgary in the winter, and 135, 140 degrees in the Saudi desert on the back end of a tank in the summer. It's a very stable material in that way. It does not absorb very much moisture at all. It's less than 1/10 of 1%. So moisture absorption is nil, whereas with, again, the cast nylons and other thermoplastics, moisture can be a problem, not just in terms of swelling, but in terms of moist, dry cycles, which can lead to degradation. This material does not suffer through that. It's UV stable inherently, so again, an excellent outdoor material. It's easy to machine. There's nothing toxic about this material, so you can machine it on a lathe. It's kind of like cutting wood, so it's a very simple material to work with. And we sell it not only as finished parts, but we do also sell it as finished tube stock and flat stock if you need to make like slide plates or pads. The next product we're going to talk about is the CJ, which is our filament wound product. Now, even though both of these are polymer composites, they have some inherent differences. Laminate wound materials, you have basically a blanket of fabric that is wetted and then wound under pressure on a mandrel and then put into an oven and cooked. That's how we make the UltraComp. With this material, we have a multiple number of strands of roving material that are coming down and feeding onto that mandrel at a very specific angle and a very specific rate. So what that allows us to do is design different strengths through the wall of the bearing material. We can make it more rigid where we need it more rigid, and we can make it more pliable or flexible where we need it more flexible. Gives us a little bit of room to move when it comes to designing for specific applications. Now with the CJ product line, it is also considered to be a very high load material. Design numbers are 35,000 psi on the CJ, a little bit lower on the line versions of the CJ, but in reality these materials can go in room temperature conditions at static loads as high as 60,000 psi. But again, for design purposes, we're looking at 35,000 psi as our compressive strength. This material has a higher speed capacity than the UltraComp does. UltraComp is fairly low because it is a highly insulative material. So we tend to use the UltraComp more for applications where it's low speed oscillating, some possible low speed rotary applications, but we prefer to keep it into low speed oscillating. With the CJ, just by the nature of its makeup, we can go to higher speeds. With the actual CJ grade, up to 100 feet per minute unlubricated, and with the line grades like the FCJ or the Super CJ, we can go upwards of 500 feet per minute, again without lubrication. We have several other liner options as well, and it really is dependent on what the application you may be looking at as to which liner material we use. But we basically work with the three conditions right now. CJ, which is a sock liner made of PTFE and synthetic fibers. The FCJ, which is a filled PTFE liner, and then the Super CJ, which is also a filled PTFE, but it is heat pressed into a supporting screen material to give us a very high strength liner material. Now, looking at some of the basic attributes of the CJ, 35,000 psi static, 50,000 in room conditions, and again we're looking at fairly conservative numbers here. Dynamic with the CJ, we design around 15,000 psi, so it's a little bit less than the UltraComp, but 15 is a very good number in majority of the applications you might run into. The interesting thing about the CJ in terms of its failure mode is it's a very, very slow process. It tends to want to crush dynamically, and so rather than just failing instantly and dramatically, it will take a long time for it to eventually get to a fail point. And so it's a very good material in terms of saving your mating hardware for a long period of time before you will really know that something's gone wrong. So that's a little point about this material that makes it interesting over and above even the UltraComp. Deflection at 35,000 psi is about 5 thousandths, which means that the actual wall deflection is very limited, and the permanent deflection or the permanent set is only about 2 thousandths. At 70,000 psi, we'll see a 12 thousandths deflection, but the permanent is only 4 thousandths. So even at the extreme loading conditions, the permanent change in the wall is very, very minimal. One of the key facts about plain bearings, and really particularly about the CJ and the UltraComp and the TriSteel for that matter, is that we pay a lot of attention to the length to diameter ratio. We want to be sure that we are working within a 0.5 to 2 range in the length to diameter ratio. What that means is that if you have, say, a 1-inch ID bearing, we don't want to see that bearing less than a 1/2 inch long and really no more than 2 inches long, because it puts a new point of contact on the bearings, and usually a very high point of contact and very minimal points. The failure mode that we see generally, especially if a bearing is out of alignment or a shaft is out of alignment, is you'll see wear at the bottom end of one end of the bearing and at the top end of the other end of the bearing. It's a very typical failure mode. So we try and keep the length to diameter very tightly controlled so that we avoid a lot of that problem caused by misalignment. The temperature range of the CJ, very similar to the UltraComp. It's cryogenic up to 350. And when we talk about cryogenic, we're talking about being able to go down to cryogenic conditions without embrittling, without cracking beyond recognition. So it's a very good material, as is the UltraComp, for very low temperatures. The thermal expansion of the CJ is very close to steel. So what that allows us to do is to run tighter tolerances. We can control the expansion and contraction conditions if you've got a broad temperature range, and much more so with the CJ than UltraComp. One of the difficulties of the UltraComp is that even though it's got a fairly broad temperature range, it is a little bit harder to control when you have a, say, 150 degree span of cold to hot. So if you've got that situation on a regular basis, like outdoor applications on ag equipment or construction equipment, the CJ is a much more stable material just inherently, so it's easier to design around. One of the interesting things about the CJ is that operating conditions will really come into play with how this bearing material wears. Some of the testing that we've done, unlubricated wear in an oscillating condition, you can see by this chart that we've got 3 different test criteria here where we've got different P ratings or PSI ratings and different velocities. And as you can see, the middle PV of 4,900 psi at a 2 feet per minute speed in an oscillation gives us a very, very low wear rate, 1.9 times 10 to the minus 10. And you can see it's almost a multiple of 4 just by making a change of a lower pressure but a considerably higher speed. A lot of this has to do, again, with the fact that these materials are thermal insulators. And so if there's no place for the heat to go, that heat becomes a source of wear and ultimately failure. So we have to be real careful about where we're applying these materials to be sure that we get good heat dissipation. And that actually comes into play when we look at some of the other factors, and we'll look at those in a minute. For rotary applications, again, unlubricated, you can see again on this chart that there are some interesting variables there. The higher the PV there, the 512 with 39 feet per minute, you've got a 12.4 K factor, and it's almost 3 times that in a condition where you've got double the speed, but 1/4 the load. So again, it's attention to details when we're designing with these materials to be sure that we're matching the material with the application, and that certainly holds true with the composites. One of the other interesting attributes is the wall thickness, and this again goes back to a couple of issues. One is its impact strength, its resistance factor, and the other one has to do with heat dissipation. You can see here that by using a 1/4 inch wall, we got 15 thousandths wear at both 40 and 60,000 cycles. Now, that is really driven by the impact and also the thermal properties of the material. Because we're using a heavier wall, it's harder to dissipate the heat out. So conversely, you look at the 1/8 inch wall, 18 thousandths wear at 250,000 cycles and 15 thousandths wear at 400,000 cycles in a second test. So wall thickness is critical, fits are critical, surface finishes are critical, understanding the whole temperature range. All of this comes into play with all plane bearings, but in particular with composites. Now, lubrication. People are always wanting to lubricate these composite bearings, and our basic rule of thumb is no, don't do it. But we know that in the cases of corrosion control, especially in outdoor applications where there's a lot of wet and mud and dirt and dust and ice and all kinds of things going on, that it's important sometimes to keep the shaft coated in some way. So what we say is use the lightest grease that you can use, that you can possibly get away with. Be sure that you are purging on a regular basis so you're not gathering abrasive lapping compound. Avoid the really heavy greases if you can, but the key here is really being sure that you purge on a regular basis. The CJs can be drilled through for a Zerk fitting. You have to be a little bit careful as you drill through the liners, but it can be done. One other thing that we would warn against is do not use fluorocarbon-based lubricants. The problem with fluorocarbon-based lubricants, obviously, is the PTFE component. And because our liners are PTFE-based, we have found that some of these lubricants can actually soften the PTFE components in the liners, and that includes the CJs and the FCJs and the Super CJ. All of those have PTFE components in the liners. So avoid at all cost fluorocarbon-based grease. Some of the thermal properties, again, operating range is cryogenic to 350. The thermal expansion I mentioned is about the same as steel. Moisture absorption is less than 0.5%. Heat transfer is always an issue with polymers. With the CJ, we've got a thermal conductivity of 1.4. If you have thinner walls, as we showed before, thinner walls have a great effect on the transfer capability of heat. Always remember too that with these types of bearings, the shaft will generally run warmer than the housing, and that's just because of a thermal lag that takes place between the housing, the shaft, and the bearing. And then be sure and pay attention to your running clearances, especially if you're running at the high end of the clearances on both your press fit. If your housing is undersized, so you've got a higher press, and then if your shaft is running on the high side of the tolerance range, it can in fact cause, through close-in, can cause a little bit tighter tolerance than we like to run with. So pay attention to the running clearances. Some of the variations I've mentioned to you already. The CJ is a wound sock liner. It's a PTFE and synthetic material. Those are the lubricating sources as well as an abrasion-resistant synthetic. We also have the F liner, which is a filled PTFE. That gives us a very, very low friction, speeds up to 500 feet per minute. The downside is that the PV is reduced down to 15,000 as opposed to the 25 or 35,000 with the CJ. The Super CJ is a nice combination material. It is also a very low friction PTFE based liner, but with that additional press screen condition, what we get is a liner material that comes very, very close to the same static capacity as the CJ shell. So it's a nice combo unit where you don't give up anything in terms of PVs by going to a PTFE tape liner. The next item on our list is the TriSteel. And again, this is a little bit different than these polymer composites in that we're talking about a metal-backed bearing. Most of the world knows these types of bearings as DUs. It's kind of become a generic terminology. DU is actually a product line from another company, and everybody in the world that is making these basically has duplicated the technology. It's a well-known technology. But we've done a few different things, and that's what we really want to introduce you to through the TriSteel. What exactly is the TriSteel? It is our trade name, again, for metal-backed bearings. The industry knows them as DU, as I just mentioned. Our TriSteel grades have either plated steel as the shell, or we also have stainless, and then also solid bronze. And then we can apply different types of polymers either to the ID for shaft bearings, or we can apply it to the OD if you need to or want to use them as piston bearings. The TriSteel bearings are made by utilizing a sintered bronze interlayer. That is the bonding mechanism between the metal substrate and the polymer. All of our TriSteels are available with or without lead. Very soon you won't be able to get them even with the lead. In fact, most of our customers are specifically requesting without the lead. So, but in those rare cases where you may think that you need lead for some reason, they are still available. Just ask. Here's some of the grades that we have. Our PM liner is PTFE with an enhancement of another fluoropolymer, PVDF. The nice thing about this particular grade is that it's a thicker liner than normal. The normal PT or DU style liner is very thin. The actual lubricating liner is only about, in some cases 0.8 to about 1.5 thou. That's your actual wear material before you get into that bronze interlayer. So with the PM, we have a thicker liner, which gives you a little bit of design flexibility. You can go back and actually bore that out a little bit if you need to get some different tolerances than what is standard. We also have a PR liner, which is calcium fluoride and synthetic fibers. We have our PTS, which is a lead-free bronze. The AC liner is our acetyl liner, and that comes with reservoir holes for boundary lubrication. The acetyl liner basically requires a boundary lubrication because it doesn't have the capacity to put off heat. It has a lower temperature range, operating temperature range. So that comes with reservoir holes and a port for a Zerk fitting so you can pump grease in there. And again, when you're using grease with polymer bearings, it should be considered really for purge purposes. Be sure you have clean lubrication in there all the time. We also have an AT grade, which is another acetyl, but we have added PTFE, and we do not put the reservoir holes in there. That is a product that we use in applications where the customer just cannot use lubrication for whatever reason. One of the big places of application for that particular grade is the ski lifts, the ski resorts. The resort people don't like paying cleaning bills for grease droplets that fall on very expensive ski jackets, so they prefer to use this particular liner with no grease, and it's a very, very effective material. The next liner material that we have is our PE liner, which is our bearing grade PEEK. This is a little bit unique compared to other suppliers in that we can offer both the PEEK liner, which has excellent temperature resistance, excellent chemical resistance, and when combined with the stainless steel shell, it gives us a very, very good material for applications in corrosive environments, things like valves and pumps and any place where you might be in contact with highly corrosive or high temperature media. And then finally the PT liner, which is our direct equivalent for the DU. It's the PTFE with the bronze interlayer. So that's the different TriSteel liners that we have. Now let's take a look at some of the specific attributes of these different liners. First of all, load capacity, and in terms of static and dynamic loads. For the most part, all the PTFE materials are about the same. They're 36,000 psi static and 20,000 dynamic. That's a good number for us to design around. With the acetyl base, like the AC and the AT, 36,000 static and 20,000 dynamic for those as well. And then finally the PEEK, a little bit higher, 40,000 static and 26 dynamic. Now, these capacities are totally dependent on the motion, the direction of motion. Oscillating and linear and full rotary all produce different conditions, primarily thermal situations. So when we look at these numbers, we need to take into consideration the direction of motion. For full rotary applications, we can pretty much tell you that these numbers are going to drop significantly. And that, again, has to do with the amount of temperature generation that we would see with these types of bearings. Even though it's a thin polymer wall within that steel shell or that metal shell, there's still a polymer barrier that has to get through to the outer shell before you can dissipate the heat. So something for you to keep in mind. As far as the velocities, again, the PTFE lined, very high speeds. In fact, the PTFE lined TriSteels have the highest unlubricated speed ratings of any polymer bearings, 1,000 feet per minute. With lubrication, you can double that to 2,000 feet per minute. For the acetyl and the PEEK lined, because those are boundary lubricant materials, it's really highly dependent upon the type of lubrication you're using. So we don't really have numbers that we apply to that directly. It's on an application by application basis, taking into consideration the viscosity and the type of lubrication that you're going to be using. In the case of the AT, which again is the non-lubricated acetyl liner, we know that we can take that up to about 100 feet per minute safely without any grease. The PV ratings on the PTFE, 50,000 is the PV rating. For the acetyl line, 80,000 with lubrication. And on the PEEK, 100,000 with lubrication. Again, the acetyl and the PEEK line are not normally designed to run without lubrication, although we do know that the AT liner, again, the non-lubed acetyl liner, we can take that as high as a 40,000 PV with a sense of safety. We have performed there very well for many applications. So where do we apply composite bearings? It's pretty basic stuff. Where you have applications where you want either zero lubrication or you want the least amount of maintenance possible. That's where composite bearings come into play. Where impact and vibration is very likely. If you've got an application that's, for instance, being pulled behind a tractor and you've got suspended parts sitting there vibrating up and down on pins, that's a place for composite bearings. Undercarriage on trains, undercarriage on over-the-road trailers and trucks. These are great places for composite bearings. Dirty, dusty, road ballast, grit. These materials all have very good resistance to abrasives. Conversely, they also work really well in wet environments, in fact submerged environments. The CJ and the UltraComp do quite well underwater. A lot of the applications are things like rudder bearings and stern tube bearings and even replacing cutlass bearings on speedboats, bow thrusters, and then up on deck, winches and shivs and all types of application on deck and also on dock. So UltraComp, CJs, TriSteels, all excellent candidates for those types of environments, wet or dirty. And I would say the majority of the applications are going to be lift and tilt and positioning devices. Usually an oscillating application. Rarely do we use composites and full rotary. That's not to say we can't, but it's primarily an oscillating type bearing. Applications in construction, ag, marine industry, material handling, cranes, conveyors, also in water and wastewater treatment facilities, hydro plants, wind power turbines, automotive components, military vehicles, railways. These are all just a snippet of some of the applications where we've utilized these products. For some picture views, here's some of the places. We've got them on dockside cranes, as I mentioned. Railway, many applications in railway. Construction equipment, ag equipment, so tillers, air seeders, composters, all kinds of applications, manure spreaders. And we've got forklift attachments, valve stem bushings and corrosive valves, trailers. We've even got TriSteels and 16 satellites that are circling the Earth right now, communication satellites. Racing boats, military equipment, right-of-way equipment. There's no end to the applications where you can apply composite bearings. And remember, as I said at the beginning, don't be scared off by the word composites. We're not talking about aerospace composites that are using carbon-carbon technology. We're talking about industrial fibers, industrial resin systems, and they're really geared towards the marketplace in terms of their cost effectiveness, also their performance. So if you've got any of the criteria we've talked about here, give us a call. I'd invite you to go back to our archives and look at some of our old shooting stars, because a lot of these applications are mentioned throughout the years in our shooting stars, so it'll give you a better idea of where and how we applied them. But in the meantime, if you have a specific question or you think you might have a place that some of these materials might be suitable, contact us through Ask the Expert. Give us a call or email us at www.tstar, and be sure and visit some of our snippet videos on our video library. There's some interesting information there on design and bearings and lubrication and friction and all kinds of different little issues that might be of interest to you. So thanks for joining us. We hope this has been of interest to you and look forward to seeing you on another Tech Talk. Thank you.